Okay, let's dive right in. Today, we're talking about a pretty groundbreaking AI architecture that's really shaking things up in self-supervised learning. It's called JEPA, the Joint-Embedding Predictive Architecture, and it's a huge step towards building what AI pioneer Yann LeCun calls world models. We're not just going to talk theory, we're going to look at the actual code that makes it all tick.
Whoa. Okay, that is a massive claim. I mean, for years, the gold standard was pre-training models on these gigantic labeled datasets like ImageNet. This is basically saying you can just toss that whole approach out the window. JEPA can learn so well just by watching stuff that it actually beats those old school supervised methods. It's a complete paradigm shift.
So the big question is how? How is that even possible? Well, the secret, and this is really the core idea, is that it completely changes the game. It stops playing the old way, which was this brute force method of trying to predict every single tiny pixel in a picture.
Right, so that leads us to our first big idea, moving beyond pixel prediction. We're shifting away from this painstaking process of reconstructing an image pixel by pixel and moving towards something way more elegant and, well, just smarter. Instead of getting bogged down in all the noisy, irrelevant details, JEPA learns to focus on the concepts behind the data.
So here's a good way to think about it. Imagine you have a photo of a cat, but part of it is blacked out. The old school generative models would try to be a master painter, right? They try to fill in every single pixel, every whisker, every bit of fur. Super hard, super expensive. JEPA? It's different. It's more like an art critic. It just looks at the blank space and says, yep, that's where the ear should go. It's predicting the idea, not the pixels.
And this is where all the magic happens. It's in something called the latent space. This isn't the pixel world you see on your screen. Nope, it's a kind of compressed, abstract world where the model thinks in high-level concepts. So it's not thinking about RGB values, it's thinking about catness or carness. And you can imagine, that's way, way more efficient.
All right, so we get the what. It predicts abstract ideas. But how does it work under the hood? What's the actual machinery? Let's take a look at the blueprint and break down the components.
So when you boil it down, there are really four key players in the setup. First, you've got the context encoder. Think of it as the part that sees what's currently there. Then comes the predictor. Its job is to make a guess about what's missing based on that context. Third, the target encoder. This one gets to see the actual answer, the ground truth. And finally, you have the loss function. It's like the referee, comparing the guess to the reality and saying how close they were. So let's trace the data flow here. You feed something into the context encoder, maybe a few frames of a video. It chews on that and spits out an abstract idea, a representation. That representation goes straight to the predictor. The predictor then makes its best guess about what the next frame's representation will look like. And at the same time, the target encoder is looking at that actual future frame and creating the real representation. The whole goal of the training is just to get the prediction and the target to be as close as they can be.
Now for the fun part, especially if you're a developer. Let's see how this whole thing looks in actual PyTorch code. We're going to peek under the hood and see how this elegant theory actually gets built.
Okay, first up, the context encoder. If you've ever worked with a vision transformer, a VIT, this code is going to look super familiar. It's pretty standard stuff. You've got your patch embed that slices up the image into little pieces, and then these transformer blocks do the heavy lifting to turn those pieces into that rich, abstract representation we keep talking about. Then we have the predictor. And check this out. It's way simpler, right? It's really just a basic MLP, a stack of linear layers. And that makes sense, because its job isn't to understand the whole image. It just takes the complex output from the encoder and tries to morph it into a prediction. That's why it can be so much smaller and more lightweight. All right, now the target encoder. This is where a really clever trick comes in. See that IMA decay variable? That's the secret sauce. See, this encoder doesn't get trained with backpropagation like the others. No. Instead, its weights are just a slowly updated copy of the context encoder's weights. It's an exponential moving average, or EMA. What this does is create a really stable teacher model. It's not jumping all over the place with every training step. This gives a predictor a nice, steady target to aim for, which makes the whole training process way less chaotic. Okay, so we've got the main parts, but there's a big potential problem. A gotcha. What's to stop the model from just being lazy? It could just learn to output a vector of all zeros for the prediction and have the target be all zeros. The loss would be 0, perfect score. But it hasn't learned a thing. This is a classic problem called representational collapse, and you need something smart to stop it. And that's where the other secret sauce comes in, a loss function called vicreg. It has 3 jobs. First, invariance. That's the obvious one. It just says, make the prediction and the target similar. But here are the 2 clever parts. Variance tells the model, hey, you need to actually use all the numbers in your output vector. Don't let them all collapse to 0. And covariance says, make sure each dimension in your vector is learning something different. Don't be redundant. It's a bit more complex, for sure, but without it, the whole thing just wouldn't train properly. It's absolutely crucial. Okay, let's zoom back out from the code for a minute. Let's talk about the big picture. Because this architecture, JEPA, it isn't just a slightly better way to do things. It's a key building block for a much bigger idea, building world models. So what's a world model? The dream is to create an AI that can actually understand how the world works. You know, reason, plan, get cause and effect. Kind of like we do. And by forcing the model to predict things in this abstract way, it has no choice but to build its own internal model of the world's rules. It basically has to learn a kind of intuitive physics, just by watching videos. And this is why JEPA is such a great fit for this goal. Look at the old generative models. They get so hung up on predicting every single detail, the exact color of a leaf, the way the wind is blowing, all this stuff that might not even matter. It makes them huge and slow. JEPA is different. It's designed to be efficient. By working in that abstract space, it learns to just ignore all the random, unpredictable noise and focus on what's actually important. That's what makes it so much more scalable and, frankly, more powerful.
Whew, okay, that was a deep dive, right? We went from the big picture theory all the way down into the nitty-gritty of the code. So let's just wrap up with the key takeaways. What are the main things you should remember from all this?
So, first and most importantly, JEPA predicts in abstract space, not pixel space. This is the big one. It's all about efficiency and high-level concepts. Second, remember the 2 clever engineering tricks that make it all work. That slow-moving teacher, the target encoder using an EMA update, and the vicreg loss function that stops the model from getting lazy. And finally, remember the why. This whole thing is a huge step towards building those world models, AIs that can learn how the world works just by watching. And that really leaves us with a pretty wild thought to end on. We're creating AIs that can learn the fundamental rules of our reality just by observing. They're not just copying patterns, they're figuring out the why. So the question is, if AI can learn the underlying rules of our world, what will it predict next?